Our speaker today is Peter Diorio. I'm going to read his little bio here that I found on the Geosoft website because they are hosting the go-to webinar today. Peter Diorio graduated from Carleton University in 1976 with an honors BSc in Geology and Physics. He started in 1976 as a geophysicist with Standard Geophysics Limited, then joined BHP in 1980 as an exploration geophysicist, working on a wide range of base metal, precious metal, iron ore, and diamond projects worldwide, and as a research application geophysicist for various initiatives, including airborne gravity gradiometry and various airborne EM developments. In 2009, he founded GeophysicsOne Inc, which specializes in processing, interpretation, and integration of geophysical data with geology. And he'll be speaking about practical methods for integrating and interpreting large-scale, multi-parameter 3D inversion models with examples from the McFauld Lake, Ontario Airborne Gravity Gradiometry and MAG survey. Now, this survey is very near and dear to my heart because I was the QA QC geophysicist for this survey. So I saw this survey grow from its pre-survey calibrations to the survey to processing to the final products. So I'm very interested to see what Peter has to say. So welcome, Peter.
Thanks, Edna, and thanks to KEGS for the opportunity to speak today, and also to Geosoft for the effort they put into putting these things online, which I think is a terrific service. The outline of the talk is as follows. I'll try and give a little bit of background and some of the geologic and exploration context. And then the meat of the talk really will be on using 3D models, or how we can use 3D models for interpretation, with an emphasis on combining MAG and gravity results, really for mapping purposes. We'll look at imaging, some classification and mainly clustering and mainly classification schemes. Look at some implications based on inversion of synthetic survey data. And then finally look at classification using the McFauld Lake density and susceptibility models. The survey that Edna just alluded to was almost 20,000 line kilometers. It's flown in August, or released in August of 2011, flown earlier, obviously. 215-meter line separation, and it was flown with then Fugro's, now CGG's Falcon system. The data include terrain-corrected gravity, GZ, vertical gravity gradient. Do I just hit OK to that? And the data sets include the usual suspects of terrain-corrected gravity, vertical gravity gradient, all the tensor components that are calculated from the measured components, TMI, and a detailed digital elevation model. Common usages of such surveys are for direct targeting and really for targets that are characterized by large tonnage and large density contrast. I'm not going to be talking about that today particularly. I'm going to be focusing more on mapping applications for host lithology, structures, and integration with other data sets. A cartoon of the exploration scenario in the region. At the upper part of the section, you'll see a thin wedge of Paleozoic, mainly carbonate cover.
So you can take a moment, we still have a bit of a technical difficulty.
Sure. All right, we're going to be focusing on mapping applications. And this cartoon section shows the exploration scenario, a thickening wedge of carbonate Paleozoic cover, thickening towards James Bay. An unconformity below that, which is sometimes conductive. And then beneath that, mainly Mesozoic Archean basement with Neo-Archean McFauld Lake fold greenstone belt, which in turn hosts a fractionated ring of fire, ultramafic to mafic intrusive. The exploration history is fairly recent in this case, and that has largely to do with the remoteness of the site and also the Paleozoic cover. So that's both a blessing and a curse. It's protected it from historical exploration. But in 2002, I guess pursuant to the discovery of the Kyle kimberlites and Victor kimberlite, De Beers and Spider were exploring for kimberlite with mag, and they discovered, lo and behold, a VMS deposit, which of course led people to suspect and later demonstrate that there was a greenstone belt, which was explored then more aggressively for VMS, and then exploring for VMS with EM and mag, they discovered not several more VMS, but then discovered a very significant magmatic nickel-copper PGE deposit.
There is a question about the size of the present-day ore of this area. What is
about 100 kilometers or so in dimensions. We're looking at more than that. 100 kilometers in terms of the survey. We're looking at more than that in terms of this cartoon. In 2008, while exploring for nickel-copper PGE using drilling, chromite was discovered, which looks like the jewel in the crown so far. And then during subsequent exploration and drilling, principally for chromite, a very large vanadium deposit has been discovered. So things always don't unfold the way we intend, but sometimes they work in your favor anyway. These two panels show the measured mag and the vertical gravity gradient data. Actually not the measured mag, but a half VD. And you can see that they're both mapping largely the same major features. On inspection, you'll see that the gravity data has the characteristic noise, that sort of orange peel texture that's endemic with that sort of data. And you can see some features right away that aren't particularly well represented on the mag image. But by and large, the features that are dense are also the ones that are most magnetic, or at least most magnetically active. And in subsequent slides, we'll look at a small postage stamp, what's referred to the Big Daddy chromite, and there's a small patch of gravity and geology data that's publicly available. Considering densities for just a moment, and these were supplied by Des Rainsford at the OGS, and based on a relatively modest number of samples, but they all seem quite reasonable. And you can see that as you progress from towards more and more mafic rocks, the density steadily increases until you get to the ultramafics. And in these cases, the peridotite, pyroxenite, and dunite all start to drop away from that curve, particularly the dunite. And the reason for that is apparently the conversion of olivine, which is present in varying amounts in the ultramafics, conversion of the olivine to serpentinite, or serpentine, and or talc. And that is accompanied by a dramatic drop in the density. And if it happens to be an iron-rich olivine, then it'll also increase the magnetic susceptibility. So these would be textbook values for peridotite and the other ultramafics, and these are the actual measured ones at the fault site. The chromite itself measures very high density, around 3.8 or so. So at least superficially, it looks like it would be a good gravity target. This is the setting of the Big Daddy chromite deposit, one of a string of deposits that I'll refer to several times during the talk. It's a fractionated, it's hosted by a fractionated ultramafic to mafic sill, intruding a granite diorite. and probably its related volcanic pile. It's steeply northwest dipping strata with tops to the southeast, so it's slightly overturned. After the initial discoveries, ground gravity quickly became the tool of choice. The deposits are not very well resolved on the airborne gravity survey, though the setting is. I'll just highlight this area of gunite on this image and then move to ground gravity here and the airborne vertical gravity gradient at the same scale. Field of view here is about 3 kilometers. The chromite deposits themselves are shown in these black outlines, and you can see on the ground gravity, despite some artifacts, it's done a pretty good job of focusing in on the features of interest. On the airborne data, despite very carefully stretching the image, you can make a case that you've detected the main part of this anomaly, but it's a tough sell. The dunite shows up as this rather erratic low on both images. And that turns out to be something you can see at a regional scale as well. So this is a 3D model, actually 2 3D models, one of density and one of susceptibility, both converted to, both calculated actually with Geosoft Boxy, and isosurfaces have been extracted. The blue ones are the dense features, and the reddish, brownish ones are the susceptible features. And you can see that the string of deposits, the one we were looking at was just in here, but the string of deposits all sit right along this contact. So at least even from the airborne data, you can get some insight into where the correct place to look might be, and that's at this particular interface. So moving now from this sort of postage stamp view to regional scale models, it's possible to generate very large inversions these days, and these are voxel models using a typical smooth model inversion, unconstrained inversions in both cases. TMI was used as input for the susceptibility model, and the 2 measured tensor components were inverted to give the density model. So the problem with dealing with something like this is each model has about 25 million active voxels in it. And the first problem is how simply do you display that in any fashion that you can use. I've cut isosurfaces out of these and displayed them like this. It would simply bring at least my kind of computing resources to its knees if you try and do anything with that. And the second issue is how do you actually capture an interpretation? You may see something of interest, but actually tagging it and doing something useful with it becomes quite challenging. And the strategy that I've stuck with is to reduce the dimensionality, which is a fancy way of saying that I'm going to slice it, and I'm going to combine the parameters in some fashion that's hopefully intuitive. So the easiest way to go is to take a slice through the models. In this case, it's 100 meters below what is a sloping topographic surface. And if you are slicing models like that, you'll be forced to, you'll certainly want to give some consideration to how you generate those slices. Over a large area, topography is almost never really flat, and it isn't here either, although it's close enough for most purposes. You'll find that the slices intersect the terrain if you do them horizontally. So you have to follow the terrain, but you generally don't want to suddenly drop down below minor ravines and such like. Anyway, that's a bit of an aside. In this case, we've extracted 2 slices, 100 meters below the topographic surface, assign a blue to red color bar to the density, and then a black to green color bar to the susceptibility, and displayed them both using typical tools. So we'll zoom in on this area, which is the one of the main areas of interest in the survey. That's this block. You can see the chromite deposits again strung along this interface that I showed you in the 3D model between a magnetic unit and a dense unit, which shows up as red. A couple of VMS deposits show up simply because they're extremely magnetic. They really not have little or no gravity expression. And this is the Eagle's Nest copper nickel PGE deposit. Looking at just that subset block again, with the chromite deposits here, and comparing this to pre-existing geology, which will have been generated from the drilling that was, the considerable amount of drilling that was done at the time, and heavily reliant on the mag. So these are not independent data sets, but you can see that there's a great deal of correlation between the two. There's also some differences which would be perhaps quite significant. In particular, some of these dense units are not captured, or not split out in the what is referred to as a presumed geology map. This is Jim Mungel's map that's all over the place.
A little louder. Please, Peter,
Yeah.
we're losing you in the back.
Sorry, this won't help, but I will try and project. Yes. Okay, so the key messages: slice and combine parameters using off-the-shelf imaging tools. It's simple, it's quick, it's relatively intuitive, and it's effective. And it lends itself to conventional regional interpretation schemes in a GIS environment, or paper maps if that's your preference. So it really serves the bill, and I have to say that's the way I treat most data most of the time. Do want to move on and look a little bit at some options as far as clustering and classifying the data. And I'll say at the outset, this is a work in progress. First, a couple of definitions. Clustering is generally considered to be an unsupervised approach where you try and group sets of objects so that objects in the same population are more similar to themselves than they, in some sense, than to objects in other populations. So an example would be sort all my email into groups by context. And that's not an easy task because we're not telling it what's important. Classification, on the other hand, is a task of assigning one object to a set of predefined populations or classes. So in the email analog, this would be to pigeonhole all the spam into my junk email, and the not spam goes to my inbox. So I've decided what the boundaries are by some supervised process, and I'm going to sort the data that way. So this is an example of clustering done by BHP, and in this case we start out with similar data, TMI and vertical gravity gradient. It's from the Musgrave region in Australia. We inverted separately, and then the inverted results were fed into an algorithm that generated some boundaries, some clusters on this scatter plot of density versus susceptibility. And then those clusters were mapped back to the cartographic space. In this case, it's actually a 3D model of these clusters. The entire mapped area is actually full. It's just been blanked out, and only the most anomalous features have been retained in this image. This is in a paper by Doug Oldenburg and Dave Pratt from Exploration 07, and you can read a bit more about it there, though there's not many details. Another example was published actually using data provided by Laurie Reed, who is sitting over there, and Des Rainsford in the Nipigon area. And this is some rather interesting work that's been ongoing by Stephen Fraser at CSIRO. And essentially the same parameters get, along with any others you care to think about, get tossed into a self-organizing map algorithm. Now the term is actually a bit misleading for this audience because the map that gets organized is not a geographic map like we normally think about. It's in this case, susceptibility density space. So that gets organized into some clusters, and then these clusters get mapped back into something that means hopefully something useful to a geoscientist. In other words, back into a cartographic map. And in this case, just one of these clusters has been plotted back on the map of the original data. One interesting aspect of this approach of using a SOM is that it does automatically an output, a measure of what's referred to as the quantization error, which tells you how far any particular element is away from the centroid of a cluster. So that gives you a measure of anomalousness, if you will, and lets you spot outliers. Perhaps of more interest if you're feeding your banking information or your credit card information into something like this than what we normally do, but interesting nevertheless. The main concern that I have with this is that it's very much a black box operation, and I've always felt that we probably have enough black boxes in this game. So how to proceed? This is a scatter plot that's extracted from a horizontal slice from a very large survey, and it's a tiny subset of the data. So, and they tend all to look like this. You can see one cluster that's more or less strung out along the origin of the two axes, and then some blurry features that spew out from there. What's a reasonable approach to group things together? We know that things group together in a meaningful fashion because we can see it on a map. Even if you plot up just susceptibility and density and put them as overlays, you can see the correlations. It's intuitive. Very hard to spot once you go into a scatter plot like this and try and cluster, or in this case, and try classifying the data. So the approach that I've taken to gain some insight into this is to build a case study using synthetic survey data, so I know the answer beforehand. And the synthetic survey consists actually of a snippet of data from the McFauld Lake area, and by data I mean only the flight path, the topography, the altitude, and the line. So the line spacing has real characteristics to it. But the actual Earth is generated using model vision, and it's simply two layers in a folded anticline with plunge towards the southwest. And density and susceptibility are different between the two layers, but they're constant along the layers. So very simple situation. Calculate forward model of mag and gravity gradient either with or without noise, and then feed that into an inversion, and you come out with some inverted models. So here's our recovered density, and again I've gone to a slice, and recovered susceptibility. And as we've come to expect, the inversions do a very good job of recovering the geometry that was blatantly obvious in the synthetic data in both cases, and it's generated more or less the correct susceptibility and density compared to the input. But even at this scale, you can see that there's some variation along the limbs of the fold, dropping off towards the nose, increasing again. And these susceptibility, or density in this case, and susceptibility here, they're both plotted with linear color schemes. So any of the variations that you can observe on here at this scale are actually reasonably dramatic. We're talking about a factor of 2 or 3 between the highest and the lowest recovered density. Not a big problem, but just an observation. So let's look at a profile that's extracted across this to simplify the amount of data that we're looking at a bit further. In this case, we're looking at just the mag data on the top, and this hasn't been pole reduced, so you can see some asymmetry from that and from the dip. And along the bottom, the heavy line is the recovered density, the recovered susceptibility along that profile. And the shaded areas are the input model. So in a perfect world with no noise, no need for invoking smoothness in the model, we would expect to recover exactly this. So everything would be 0, except for here it would be 0.1, here it would be 0.05, 0.05, and 0.1. You can see that it's done a very good job, again, exactly as you would expect. Small overshoots at those 3 points where the recovered density is slightly higher than the input model or the control case. But everywhere else, the susceptibility is actually lower than the input. So that'll have some implications when we start forming clusters with classifying this data. Adding the GZZ data in blue, data on the top, and the models shaded in a similar fashion in blue on the bottom. Again, you can see there's only small places, similar locations where it overshoots. And the shapes of the recovered density and the recovered susceptibility are very similar. The amplitudes are different, but the shapes are very similar. In other words, you can see that this one's overshooting at the same spot that this one's overshooting. But almost everywhere, the recovered density model will be slightly depressed from the actual density model. That may be intuitively obvious to everyone. It certainly wasn't obvious to me. So what are the implications of this if we put it back and look at it as a scatter plot? So I'm going to go back to the original, in this case, just that slice of data, take all those data points in that slice and put them into a scatter plot of susceptibility and density. These were the two values that were assigned to the sus and dense for the outer and inner folded layers. And this is the scatter of density and susceptibility that's recovered from that. It appears that there's no data right down in here. That's actually a very high value, close to 0. You can see it's done not a bad job of putting the highest point close to where we want it, but the dominant feature is actually a streak that goes from something close to the actual value down towards 0. And I think based only on this we could get some insight into the way that any sort of classification scheme should be structured. In other words, we want to be looking for or isolating things that are joined together along these radial bands. I've kept exactly the same model, but I've assigned a different density, in this case a negative density contrast, to the outermost band, to one of the bands. And I've also relaxed the lower bound and removed the lower bound from densities. Since I have negative density in the model, I want to be able to recover that. And by doing that, it's created a bit more scatter in the plot. But we still have the same sort of largely dominantly radial pattern emanating out from 0. The axis of this feature has also rotated somewhat towards the 0 density plane. Same with this one compared to the previous example. So we can see we're doing a poorer job now of recovering the actual ratio, but we're still getting something that would cluster together with a similar sort of set of, I guess, geometric aspect in this display. And finally, going back to the original model, same density and susceptibility in the input model, but in this case I've inverted GZ instead of the gravity gradient. And we can see the general form is similar to the very first one, with the two rabbit ears pointing towards the expected values. But again, we're seeing a bit more rotation towards the lower, towards the 0 density plane. And that's because the input data is somewhat smoother, and no matter how tightly I tried to fit that relative to the noise, even grossly overfitting it, still got the same rotation. So my expectation from this is we're not going to do a very good job of recovering the actual density susceptibility ratio, but we can group things together in a similar fashion as long as we keep the inversion parameters similar. So this is the scatter plot I showed before, and what I'm suggesting here is we should look at classes that are shaped like this. Without knowing what the boundaries of those classes are, we should expect to see things that are shaped more or less like this. If we had a population that had very high density and very high susceptibility, they might plot up here outside the range of this plot. But we wouldn't particularly ever expect to recover a cluster of features sitting like so. So let's take the little bit that we've learned here and see if we can apply it to McFauld's lake data. Now, in this case, I've generated the classes based on the simplest possible boundaries that one could imagine. So basically divided up the densities and susceptibility space into octants, separated by 45 degrees, and assigned similar colors to adjacent classes, which turns out to be rather important in terms of just the way you assimilate the data in a lot of cases. If you use glaringly different colors, it can be quite distracting, to say the least. And I've used brighter shades have been assigned to the more anomalous classes. So I've ignored this part here entirely. These are subdued. They're actually just masked out with a transparent mask, and you can adjust the dimensions of that relatively easily. These are, in this case, it was actually GNE and GUB and TMI. Okay, I will do that. So here's the process of applying the classification scheme. A MagSus model, a density model. So for each voxel, you'll look up density and susceptibility, and then recover that back to a classified, apply that back to a classified model. simply through coloring. Again, displaying the same area we were looking at earlier and looking at a 100-meter depth slice. You can see some of the deposits in here. These are the various VMS deposits, most of which show up as red blobs, similar to the greenish colors I think they were on the image, which shows very similar data. The various chromite deposits along here, the Thunderbird vanadium deposit sitting in here, and the nickel PGE deposit here, as well as another chromite deposit. So let's look at the classification for an area centered on this belt of chromite deposits again. For reference only, the small geology image that we referred to earlier here around the Big Daddy deposit that sits in like so. But we're going to be looking at this area and adding the classes in one at a time. So class, what I've labeled class 9, which is modest density but highly magnetic. That forms the footwall to all the deposits. And that's dunite with its density depressed by serpentinization. Skipping over to class 11, we see a dense but relatively weakly magnetic intrusive rocks, probably pyroxenite. And these form the stratigraphic hanging wall. And perhaps surprisingly, a very thin layer, presumably peridotite and chromite, maps into class 10. And that does not identify. It coincides with all the chromite deposits. Low density and high susceptibility, class 16 is inferred to be the highly altered basal part of the intrusion, presumably related to the dunite. This class actually is globally rare, and it's also associated with the Eagle's Nest deposit, which isn't particularly surprising since it's peridotite thought to be from the same intrusion. Low susceptibility and moderate density, class 12, maps the gabbroic upper part of the intrusion and the related mafic volcanics. And finally, the felsic and intermediate volcanic and intrusives are inferred to dominate the relatively low density and low susceptibility classes, 13 and 14. So I hope I've been able to demonstrate that despite an extreme simplicity and arbitrary nature of the classification scheme using just these 8 arbitrary classes, a surprising amount of geologically meaningful information can be extracted. Refining these class boundaries with hard geologic control was an obvious next step, but that's a tale for another day, and I'll close off here. Summary. Integration of multiple data sets by inversion and either imaging or classification is a powerful way to gain geologic and exploration insight into complex data. I think this should be applicable to methods which investigate similar volumes of rock, i.e. You've got some hope with combining mag, gravity, resistivity, modern EM systems, but not, for example, mag and radiometric data. This is essentially empirical. I want to emphasize that these are interpretation tools. They're not interpretations. You're still going to have to apply some insight and some geologic feedback into things, or it becomes worse than pointless. Definitely a work in progress. need to refine class boundaries with geologic control, as I mentioned. I have dabbled some time ago with automated radio classification, the radio clustering. So that's an avenue that could get away from some of the arbitrariness, or maybe that's just offloading the arbitrariness of the boundaries onto some boffin who works out the algorithm. And then add EM inversion data or results into the mix as these things are becoming more and more readily available. Thank you very much. Again, thanks to KEGS and Geosoft, and I'd like to acknowledge in particular Ken Witherly, Conda Consulting, and various others for their help and support with this. Throw it open to any questions.
Is there any data available over the internet?
There's publicly available? Oh, yeah. The question was, is there any EM data available over the area? And Ken actually has spent a fair bit of effort in trying to secure publicly available data, and there's postage stamps available, but nothing like contiguous surveys. And part of that has to do with the history of the project, although there's a lot of data been acquired. A lot of it is sitting in reservoirs. So short answer is no.
Can you go back to, you had one map, you had an area, or a class 9 and a class 11, which basically fall on either side of the chromite.
Yeah.
And then you have class 10, which is intermediate characteristics from 9 and 11, and it falls in the sort of the boundary between the 9 and the 11. But how do we know it's a distinct class as opposed to just a smoothing of the characteristics?
It probably is just a smoothing. In other words, I don't think that that this is actually showing you anything different than the chromite sits at the contact between those two classes.
Sure.
I believe that's the case. If that was completely unique in the field of view, then I think you could draw some other assumptions.
You could say it's still a contact finder, which is pretty relevant as well.
Have they explored any of the other purple lineaments?
I have not done any exploration personally. I'm not involved in exploration in this area, and I'm sure a lot of the various anomalies in here have been quite thoroughly tested. Sorry.
I'll read you questions online. Diego Vasquez is asking, what software was the inversion algorithm used?
The question is, what software was the inversion done with? And in almost every case that I've shown here, it was done with Geosoft Boxy.
Next question. There are a few.
There's a few now.
Yeah, could you comment on how you did strip off the overburden, topo, and the carbonate platform?
The question was, how did it strip off the topo, carbonate platform, and what was the other one? Overburden. Essentially, you don't. They all appear as noise in the data set.
You don't get a nice green color that would be low density.
You'd like to think that you could recover a thickening, a gradually thickening wedge with potential fields. And with these sorts of inversions, you certainly cannot. I've tried many times, and for applications like coal and such like, it's very important to be able to map thin horizontal things. It's rather terrible at it.
These maps you're showing, are they taken at a specific depth? But some of your graphs were at 100 meter depth.
I think all of them were at 100 or 200 meter depth.
Oh, so you might
This one was.
basically looking at
It's not.
the carbonate.
It's not there.
Yeah.
You just don't see it. You'll see if the wedge is increasing dramatically or your altitude is increasing dramatically, then you'll see a blurring of the higher frequency signature. That's sort of intuitive, but you tend not to see and not be able to recover that. And I think that's inherent in the fact that these things don't, the airborne data doesn't recover long wavelength very well. So there's not long wavelength density data in there. The mag is largely, those sorts of features are largely invisible to the mag. And then we're generally subtracting a median or mean from the data when you start off, and all that goes away as soon as you do that. Gordon.
If you were to inspect the voxels of the susceptibility or density as a function of depth,
Yes.
are most of the, does the inversion tend to put most of the features near vertical?
The question is, if you look at the voxels as a function of depth, do most of the features appear near vertical? And I would say, as a general rule, I'm just trying to find as a general rule, with the unconstrained inversions, even if there's known to be fairly dramatic non-vertical dip, things tend to rotate pretty dramatically into the vertical sense. So if you look at various slices through these, and I should have included a slide like that, what you'll see is the high frequency information is in the shallower slices, and things gradually get blurrier and not necessarily less amplitude in terms of the physical parameter, but the frequency content drops off. So it's probably a very expensive filter, computationally expensive filter, but it's quite effective as well. So the reason that I've used not the zero depth is a lot of the noise, say in the gravity data, is accumulated in that shallowest depth. This is probably truncated just to show those images, truncated at 50 meters or something.
Do you find the ratioing process, does it treat artifacts and do you have to remove them?
The question was, does the ratioing process create artifacts and you have to remove them? I'm not actually ratioing any data. Okay, all I'm doing is deciding on a density susceptibility space where the boundaries are going to be, and then plotting the data according to the colors that I've assigned to those. It is akin to a resistivity, a ratio, but it doesn't have any of the sorts of singularities that you'll, by dividing by zero or very low numbers or anything like that, you're more or less protected against that. I'm eliminating, displaying some of those features by not plotting things that are right at the origin. Other than that, even those, if you plot them, plot smoothly into the rest of your data.
There are a bunch of questions from the audience. Najiko Gumi asks, can we apply this clustering to other type of data, in brackets IP, RASI, and
Well, I think you can, subject to the comments on my very last concluding slide. They have to investigate similar volumes of data. Otherwise, you're increasing the amount of uncertainty enormously. And by going to, I mean, it's challenging enough, as I think you can see, just using very similar data inputs like gravity and mag. If you go to surveys which have very different survey response parameters, then I think you'll have even more challenges. But in principle, it can certainly be done.
there is a similar question from Sergio Espinoza. from Ivanhoe. And he says, have you tried such classification using mag and gravity as opposed to gravity gradient? And if so, do you have problems with the differences in the wavelength?
The question is, have you tried using gravity rather than gravity gradient for classification? And I have on occasion. You can see the effects in one of the slides where I plotted a cross plot of density calculated from GZ versus susceptibility, the third of the synthetic examples of a cross plot. And yes, you do have issues with differences in the wavelength in the input data. Doesn't create artifacts, but it will change where the boundaries occur.
Next question, Eddie James asks, what software you use for the radial classification?
That was, almost all of it was done inside Geosoft, just by importing data from the models into what turn out to be very large databases, and then simple manipulation, very simple arithmetic from there on.
Joseph Islas, are there any questions? Should I keep going?
If this survey had been done before 2002, I assume you would have found, we would have found the VMS deposits. What else could we have discovered as a primary targeting tool using the mag and gravity gradient data?
That's a really good question. I'd probably turn that one over to Edna to answer. You thought a lot more about the data set than.
Maybe just to see if it was good quality from what was being shown.
I think he would look at the chromite anomaly because it would look strange in the context of everything else. Very strong gravity.
Yeah, certainly that intrusive would have attracted attention.
Yeah.
That begs the question, are there other big chromite deposits around Northern Ontario in particular that no one's really looked for until we acquired it?
I have to remark on, I didn't know enough about it. Obviously I still don't, but I know a lot more. And it's remarkably similar in the geology to the classic photo deposit, which is proterozoic chemistry, Archean. But the low density, weathered or altered dunites, the chromite, which are there, they're not perhaps as big. There's chromite all along. Everything is along old strata like this. Tyler was working there in 1959 on geophysical survey. He's trying to figure out why there was a negative gravity anomaly all along the belt. And exactly the same reasons. So yes, this is not unique geology.
No, it certainly wouldn't presume that it was here.
I asked Gordon, was there gravity showing the chromite in our compass?
No, I
It was
don't.
positive.
I don't believe so. There were density measurements, so
Yeah.
positive, but I don't think the chromite bands were thick enough to have a big effect. But there were ultramatrix that were dense, but there was a serpentinite bands. They were very positive that what they were doing. They could trace the geology for tens of kilometers, and but only some parts of the section had massive sulfide deposits. And the interesting thing is that the massive sulfide deposits were only in sections which showed gravity low because of the serpentinization. And they, once they discovered that, they didn't find two smaller deposits to the east.
Jerry.
Here, a very nice exposition on the power of 3D inversion and astutely applied.
Power of PowerPoint, you mean?
But of course, what you get out of the inversion machine is a function of the resolution of the data that went into it. So if you would go back, way back to where you showed ground versus airborne, the AGG. Yes. I wasn't sure what system you were comparing and what the amplitude of those features were.
Good question. The airborne system and data is from the Falcon, the regional Falcon survey. Okay, so it's the same data as we've been looking at everywhere else. These would be tens of ETFOS, perhaps 50 ETFOS from memory. Sorry, I put this slide together a couple of years ago.
50, you said. 50?
Yeah, and that's pretty much a guess. Any comments from anybody else?
And the ground?
And the ground, what you're looking at here is about the extent of the information that I have on the ground gravity. In other words, here there be colored spots. Okay. No idea of what residual or what regional has been removed or whatnot. These are, you know, as you can see on the fine print here, it's taken from an NI 43-101. So
really, the scrutiny of the 43-101 was deficient and didn't require any details.
Yeah. There has been a regional taken out of the ground, haven't there?
There has been a regional taken out of it, but there's no mention of what the regional is.
Oh.
So it might be a local filter. It just says it's a residual.
Yeah.
And would you think the gravity gradiometer technology has improved somewhat since the data that survey? To the extent that you might actually do a better job now?
Well, I think you could do. I'm sure you could do a better job with either a blimp or a helicopter system. So the hardware stays largely the same, but you can fly lower and slower. Although a blimp might be challenging these days. In the winter.
Joseph is asking if there were other geologic controls affecting the mineral emplacement, such as faulting and fracturing.
I'm sure there were. I'm also sure I don't know them.
And there is another question by a couple of people asking what type of proof do you have, like, you know, truth with the drilling?
There's very little ground control here. The extent of the information that I have available is really tied up in the map and the map of Jim Mungo that I showed as an overlay. So that's about the extent, and that's largely an interpretive map controlled along certain areas by drilling. So it's all pretty sketchy.
A question by Amobi Ekwe. He's asking about the size of the area that you inverted and a general idea of how long did it take to invert.
The size of the area is roughly 100 kilometers in dimensions.
Probably in points?
It would be about 1,200 voxels on a side, something like that. It was done in, as I recall, in 3 pieces, and they were spliced together, 4 pieces, and they were spliced together.
And how long did it take?
Each run would run overnight. So start it and an answer comes back sometime a few hours later at most.
Another question, Richard Kellett is asking, does the cluster scatter reflect the difference in resolution between the mag and gravity inversions?
Yes, I think it does, or at least the shift between away from the expected value or the input value reflects the difference in quality. You have to go to considerable effort to match the wavelength, if you will, or how well you fit the data. In other words, if you have really good mag data and fit that very tightly, say from a low altitude 50-meter survey, and fit that to the extent, to its limits, and then tried to marry that to, say, 300-meter line spacing, high altitude gravity gradient data, then you would have quite a bit of trouble. I think you'd have to degrade the mag data horribly, obscenely, in order to get something that made any sort of sense.
There are a few more questions. Is there anything on from the floor?
Yeah, there's one more.
Just a really general question, actually. Is this area being produced? Like, are those VMSs actually being mined?
The VMSs, the question is there any production in the area right now? The VMSs are all quite small, and I won't comment on whether they're economic or not, but they are quite small. The chromite deposit collectively, I've heard numbers as big as 200 million tons, but it's balkanized a little bit still. But, and the nickel PGE is quite a large deposit. It has a very small footprint, but it goes down more than a kilometer. Right now, the whole play is tied up a bit in logistical / political / land claims. Can I use the word quagmire? But it's difficult. Cliffs, Natural Resources, who are the biggest player, about a year ago now, suspended their exploration development work, continuing on with trying to move things forward, but you're in a very remote area, you've got to build hundreds of kilometers of road or railway, you've got people taking up land positions that may prevent or inhibit progress. So it will be developed, I've no doubt, at some point, but it is nothing's under in production right now. Or anybody else in the there's probably people here that are far closer to the exploration scene than I am. Any else comment?
Well, I think you've said it right. But it's awaiting decisions on access, and there's hang-ups because of one of the original groups in there. There's surface rights that's preventing access and wants more of them than really deserve. That sort of thing. But there are economic bodies there. If the access is there.
Yeah.
I'm just curious, is chromite associated there with platinum magnetite? Because I saw over there in your report, because it can happen, and it does happen sometimes, that they come in together, and then you detect indirectly chromite by detecting the type of the magnetite.
I mean, I'm sure the question, if I have it correct, is there a physical relationship between the chromite at the site and titano-magnetite? And I suspect there is. The chromite itself is pretty high grade in places. So it seems to me that it's ranging up to around the 50% Cr2O3. So I don't know how significant the other spinel minerals would be. I don't know. There's people that know the answer to that one. I'm just not there.
The one piece I know is just chromite, and titanomagnetite is not that's Big Daddy. But that's a small section of the whole thing. I don't know the rest of it.
It's a layered mafic ultramafic complex, so you've got a lot of things going on, and even where the chromite kicks out, I mean, it's not just sitting at the base of a sill, something else is going on. From what I understand, it's a fairly complex process that is required to be invoked before you can actually get a lot of chromite occurring in one spot.
Next, this is Margaret that writes, she's asking, have you tried principal component analysis or cluster analysis?
I have not. Cluster.
David Kozer is asking, would your technique apply to coal exploration?
Would it apply to coal exploration? I guess maybe. Resoundingly maybe.
Another kind of question along those lines is your classification in any way similar to neural networks?
Is the classification anywhere similar to neural networks? And the answer to that is no, though I think you could find some affinities between some of the clustering examples that I showed and neural nets, although the machine learning people would definitely say there's a big difference between a self-organizing map and a neural net. But that's the basket that I would put the neural net approach into, is the automated clustering.
Next, Eric Steve is asking if you have tried IORI focus.
The question is, have you tried IRI focusing? And the answer to that is yes. But for the purposes here, I was deliberately trying to keep things as generic and as simple as possible on the inversion front. In other words, I just wasn't I wasn't looking for any more complexity in terms of the number of input variables that I had. So I did not use IRI in this particular case.
Spell what IRI stands.
Sorry, iterative reweighting inversion. Do I have that right? Yes. So inversion. So sort of take one inversion and feed it back into the process and sharpen things up.
Can I go again?
Can I go?
No. There are so many questions. I can give you the questions. You can answer them later. Diego Vasquez is asking how many software packages you use for this presentation. Maybe it was mostly one package.
Yeah, almost everything was done with Geosoft and ArcGIS and PowerPoint. Got to give Microsoft there. Too.
Another question, when you plot the final maps, you plot the normalized value or original value?
In the example I've shown here, I've used only the original values, but that benefits from the fact that susceptibility and density are in similar ranges. It's common to have wildly different ranges in terms of the susceptibility and the density. It's really just fortuitous that both are high and similar in the case of the chromite areas.
There are a few, but there's a lot of overlap with what I already read. I'll read this last one and I can give you all the other questions.
Okay, that's probably good.
Last one. Would the terracing function on the inversion help to smooth the edges? That I'm not sure.
Yeah, I'm not sure I understand. The question is, would a terracing function help?
Make the scatter analysis work.
Yeah, I don't know. And terracing function can mean different things to different people, and I may not even be conjuring up the correct response to that. So I'll put that down.
Okay. I'll give you the rest of the questions, and with the name of the people, and you can see we can post the answers.
Okay. Well, thank you. Thank you very much.
Thank you very much.